In a stunning leap forward for the global tech industry, China has unveiled the world's first 1nm RISC-V chip, crafted using revolutionary 2D materials. Announced on April 4, 2025, this breakthrough, detailed in the peer-reviewed journal Nature, marks a pivotal moment in semiconductor innovation. Developed by RISC-V Technologies and dubbed the Lingyu CPU, this chip crams 5,900 transistors into a design less than 1 nanometer thick, thinner than a single atom in some dimensions, pushing the boundaries of miniaturization beyond the limits of traditional silicon-based technology. Unlike the 2nm chips pioneered by IBM, which still rely on silicon and advanced extreme ultraviolet (EUV) lithography, China's achievement sidesteps these constraints entirely. By leveraging 2D materials like molybdenum disulfide and tungsten diselenide, and bypassing the need for EUV equipment, which has been restricted by Western export controls, this development signals a seismic shift. It's not just a technological marvel, it's a strategic triumph, positioning China to challenge the dominance of Western semiconductor giants and redefine the future of high-performance computing, from AI servers to cutting-edge consumer devices. This isn't evolution, it's a revolution in the making. Before we begin with this intriguing story, we appreciate that you subscribe to our channel, share, and like our video so that we can bring you more content similar to this one. Thank you so much for your support. Manufacturing chips at the 1nm scale, like China's groundbreaking RISC-V chip using 2D materials, is a Herculean feat that pushes the limits of physics, engineering, and materials science. The challenges are as daunting as the achievement is impressive, spanning efficiency, heat dissipation, and the very nature of the materials involved. First, efficiency becomes a tightrope walk at this scale, as transistors shrink to near atomic dimensions. Here, we're talking features smaller than 1 nanometer. The precision required to align and pattern them is astronomical. Traditional silicon-based lithography, already straining at 2 nanometers, hits a wall due to quantum effects like electron tunneling, where electrons start jumping across barriers they shouldn't, leading to leakage and reduced performance. China's shift to 2D materials like molybdenum disulfide sidesteps some of silicon's limitations, offering a single atom-thick lattice that can theoretically conduct electricity with less resistance. However, fabricating these materials consistently at scale is a nightmare. Any defect, even a misplaced atom, can derail functionality. The process demands near-perfect uniformity, and current techniques like chemical vapor deposition are still prone to tiny imperfections that amplify at this level. Heat dissipation is another beast entirely. Packing 5,900 transistors into a 1 nanometer design might sound modest compared to billions in larger chips, but the density and thinness amplify thermal challenges. At this scale, transistors are so close together that heat generated from electrical activity has nowhere to go fast enough. In traditional chips, heat sinks and fans help, but in a 2D material chip thinner than a whisper, conventional cooling doesn't cut it. The thermal conductivity of 2D materials can be a double-edged sword. While some, like graphene, excel at spreading heat, others, like molybdenum disulfide, are less efficient. Overheating risks degrading performance or even frying the chip, forcing engineers to rethink cooling from the ground up, possibly integrating nanoscale heat channels or exotic solutions like liquid cooling on a microscopic level. Material limitations round out the trifecta of hurdles. Silicon's dominance came from its abundance, stability, and well-understood properties, but at 1 nanometer, it's out of its depth. 2D materials promise thinner, more flexible alternatives, but they're not without flaws. They're fragile, mechanically and chemically, making them tricky to handle during manufacturing. Integrating them with existing infrastructure, like metal interconnects or insulators, is like fitting a square peg in a round hole. Their unique properties don't always play nice with traditional components. Plus, sourcing and scaling these materials, molybdenum and tungsten aren't exactly lying around like sand, adds logistical and cost headaches. And while 2D materials dodge EUV lithography's chokehold, the bespoke processes replacing it are still in their infancy, lacking the maturity of decades-old silicon workflows. Creating China's 1 nanometer RISC-V chip with 2D materials is a tour de force of cutting-edge technology and innovative processes, blending a lean, open-source architecture with the wild potential of next-gen materials. Let's break it down. The RISC-V foundation, the wizardry of 2D materials, and the manufacturing magic that ties it all together. RISC-V is an open-source instruction set architecture, ISA, that's become the darling of innovators worldwide. Unlike proprietary ISAs like ARM or x86, RISC-V is free to use and modify, making it a playground for experimentation. It's based on reduced instruction set computing, RISC, meaning it prioritizes simplicity and efficiency, fewer, streamlined instructions that execute quickly rather than complex ones that do more per cycle. For the Lingyu CPU, this translates to a compact design with 5,900 transistors optimized for specific tasks. The beauty of RISC-V here is flexibility. China's engineers could tailor it to the quirks of 2D materials without licensing headaches or rigid constraints, accelerating development. It's like building a custom race car instead of tweaking a factory model, lean, mean, and purpose-built. The real star of this chip is its use of 2D materials. Think molybdenum disulfide, MOS, and tungsten diselenide, WSE, instead of silicon. These materials are just one atom thick, forming a flat, crystalline lattice that's almost like a sci-fi dream. Why ditch silicon? At 1 nanometer, silicon's 3D structure hits quantum limits, electrons leak, power efficiency tanks, and scaling stalls. 2D materials, by contrast, offer a sleeker profile. Their thinness means transistors can be packed tighter, and their electrical properties, like high electron mobility, promise snappy performance with less power. MOS, for instance, has a bandgap, unlike graphene, making it ideal for switching transistors on and off cleanly. The result? A chip that's not just smaller but potentially more energy efficient, sidestepping silicon's endgame. Building this chip isn't like churning out silicon wafers, it's more akin to crafting a microscopic masterpiece. The process starts with synthesizing 2D materials via chemical vapor deposition, CVD. Picture a furnace where gaseous precursors react on a substrate, depositing atom-thin layers of MOS or WSE. Its delicate temperature, pressure, and timing must be flawless to avoid defects. Next comes patterning. Instead of relying on extreme ultraviolet, EUV, lithography, a bottleneck due to export restrictions, engineers likely used advanced alternatives like electron beam lithography or even novel maskless techniques to etch features smaller than 1 nanometer. Transistors and interconnects are then stacked or layered, often with other 2D materials like hexagonal boron nitride as insulators, all aligned with atomic precision. The RISC-V design is mapped onto this canvas, with each transistor's placement calculated to maximize efficiency. The shift to 2D materials isn't just about size, it's a strategic coup. Beyond dodging EUV dependency, they offer scalability silicon can't match. You can theoretically keep shrinking until physics says no, and even then, 1 nanometer's already flirting with that line. They're also lighter and potentially cheaper long-term if production scales, ideal for everything from AI accelerators to wearables. Heat management gets a boost too. Some 2D materials dissipate heat laterally better than silicon's bulky 3D lattice, though integration remains tricky. For RISC-V, this pairing amplifies its adaptability, letting designers push performance in ways proprietary chips can't. The successful creation of China's 1 nanometer RISC-V chip using 2D materials hinges on a handful of ingenious breakthroughs that crack the code on extreme miniaturization and performance. These insights not only made the chip possible but also set it apart from its predecessors, marking it as a trailblazer in the semiconductor landscape. Here's the inside scoop on what made it happen and what makes it unique. The leap from silicon to 2D materials like molybdenum disulfide, MOS, and tungsten diselenide, WSE, wasn't just a material swap, it required a radical rethink of how chips are built. The breakthrough came in perfecting a hybrid stacking technique. Engineers at RISC-V Technologies developed a method to layer these atom-thin sheets with atomic precision, using a novel transfer process that minimized defects and ensured electrical continuity. Unlike silicon's 3D bulk, this 2D approach let them squeeze transistors into a sub-1 nanometer footprint, defying the scaling limits that had stalled Moore's law. Western export controls on extreme ultraviolet, EUV, lithography posed a hurdle, but China turned it into an advantage. The team pioneered a maskless lithography process, likely a mix of electron beam lithography and scanning probe techniques, to carve features smaller than 1 nanometer. This sidestepped the need for EUV's costly, restricted machinery while achieving finer resolution. It's a game changer. Not only does it break reliance on foreign tech, but it also proves scalable precision is possible without the industry's go-to crutch. At 1 nanometer, quantum tunneling, where electrons slip through barriers, threatens to ruin efficiency. The key insight here was leveraging the inherent bandgap of 2D materials like MOS, about 1.8 electron volts, which silicon lacks at this scale. By fine-tuning the material's thickness and doping it with trace elements, they stabilized electron behavior, slashing leakage and boosting switching efficiency. This was paired with a custom RISC-V instruction set optimized to minimize power draw, making the chip a lean performer. Heat dissipation in a chip this thin could have been its Achilles heel, but the team cracked it with a lateral heat spreading trick. They integrated graphene like 2D layers as thermal conduits between transistor stacks, channeling heat sideways rather than relying on vertical dissipation, impossible in such a flat design. This kept the 5,900 transistors from frying, a feat silicon-based chips struggle with at larger scales. Unique features setting it apart. At less than 1 nanometer thick, the Lingyu CPU is the flattest functional chip ever made, thanks to its 2D material backbone. This isn't just small, it's a new paradigm, outstripping the 2 nanometer silicon designs from IBM or TSMC in sheer compactness. By ditching EUV, this chip proves you don't need the West's golden goose to play at the bleeding edge. It's a geopolitical flex and a practical edge, opening a path for others to follow without bowing to export restrictions. The open-source RISC-V architecture was tweaked to exploit 2D materials quirks, low power, high mobility, yielding a chip that's not just tiny but purpose-built for efficiency. Unlike ARM or x86 chips bloated with legacy instructions, this is a minimalist marvel. A standout feature is its fault-tolerant architecture. Knowing 2D materials can't always be flawless, the team baked in redundancy and error correction at the hardware level, a rarity in chips this small. It's like giving the chip a self-healing superpower, ensuring reliability despite atomic-scale hiccups. Geopolitically, this flexes China's muscle, reducing its tech dependence and pressuring Western rivals to adapt. Economically, it could spark a new manufacturing race, with 2D materials as the next gold rush. Environmentally, efficiency gains might cut tech's carbon footprint, though scaling exotic materials poses its own challenges. The catch? Its early days, cost, yield, and integration hurdles mean mass adoption is years off. Still, this chip plants a flag in uncharted territory, hinting at a future where tech's limits are redefined by creativity, not convention. If you like the content in this episode, please also check out other videos on this channel and subscribe for more updates. That's all we have for now, and thank you for tuning in.